and today we're going to be talking about difference testing as part of sensory analysis for food product development. And difference testing is a lovely and really straightforward method for being able to tell if a product that's newly formulated is the same or if it's different from a benchmark or a baseline product. So in this video, you'll have a lot of different learning outcomes. Don't be afraid of all these learning outcomes because it will make a lot of sense as we're going through. But you'll be able to discuss when difference testing is used by product developers as a means of evaluating if a product is the same or different from a benchmark sample. We'll use a basic triangle test method for evaluating difference in food products. We'll define the correct hypothesis testing for triangle tests. We'll know what's required for setting up a basic triangle test, including the tray setup, labeling, and questionnaire scorecards. We will read the scorecard and interpret the individual results, and then use a data table for evaluating the statistical significance of the population results. And we'll get to know the role of significance in type 1 and type 2 errors. So, when you think about sensory analysis, so often we talk about tasting food products, but there's a lot more depth behind that. When we're tasting a food product, there's so many different core questions that can be asked. Is this the same or different from a benchmark product? Describe the flavor profiles. Or how much do you like this product? Each of these styles of sensory are linked together, but they're very different. So I always, when I'm teaching sensory, ask the students and ask the participants to really hone in on what is the question that's most important for you to solve to be able to move ahead with your problem solving and your project management. And so in the case of difference or discrimination tests, the key question is, are these products the same or are they different? And that's our hypothesis. So basic setup for difference test, you're typically going to be looking for around 20 to 50 panelists. But again, it really depends on the scenario. If you are doing a difference test for the purposes of putting out a scientific research paper, you may need to be doing power studies to identify how much population you need to be really authenticating your data. Whereas if you're working in private industry and you're not going to be out there publishing your data, and depending on where you are in terms of the decision making, you may be just working with an internal small group panel, perhaps of your own team or people that you're pulling from your own management group to be able to assist you. And so these numbers they're there as a recommendation, but different organizations treat these numbers slightly different, with private industry often going smaller unless they're making multi-million-dollar decisions. You do want to screen your participants to make sure that they can really differentiate flavors and aromas. So you may have a pre-screening question to make sure people don't have cold or have some sort of upper respiratory tract infection. Some people just are also just really bad at smelling and tasting differences in products, and you may want to find ways of politically selecting them from not participating in your project. So the analysis for these studies is pretty straightforward because for the most part, most entry-level users, most beginning users use data tables. And these data tables are helpful because, one, it doesn't require a lot of advanced mathematics. Two, it helps you deal with the fact that when you're doing this type of sensory analysis, people can be guessing, and they may be guessing correctly. And so we do want to account for that as part of the analysis. Triangle testing is really quite elegant and simple, and it's one of the most useful tools for early stage product development to figure out, especially if you're doing some sort of benchmarking against a standard product. That said, there's limitations. It only tells you the difference in this product. Is it the same or different? It doesn't tell you about how much people like it, and it doesn't describe any of the aromatic or flavor profiles that are in there. So you have to be really aware of that. So why would food scientists use this? Well, there's a number of different scenarios. Oftentimes it's when food scientists are adding vitamins or minerals or fortification. Maybe they're adding a technical ingredient like a shelf life enhancing additive, or maybe they're switching from the classic chemical based additives to more natural clean label additives to get that same functionality. Maybe you're changing an ingredient supplier and you want to make sure that the new ingredient has comparable functionality in the final product. Sometimes, say for example, this macaroni and cheese is a good example of where you're copying a competitor's product, or perhaps this Coca-Cola, where you've got a standard, really well-established brand for Coca-Cola, and you want the alternative formulations to be as close as possible. So low fat, low salt, low sugar versions of food products, oftentimes too, these are products that have a really strong identity within the consumer. And as a product developer, you want to have that product to be as close as possible to make sure that there's not going to be confusion when that new product is introduced into the marketplace. Now, reminder, I'm going to drill this into you. The only question that a triangle test or a difference test in this case is asking, are the samples the same or are they different? We are not asking how much do you like it. We're not asking if you taste vanilla or cone flavor or purple spot flavor. We are asking, are they the same or are they different? You'll notice here that I have 3 samples in there very intentionally, because a triangle test, as you can guess from the leading of the words, implies that there's going to be 3 samples. Triangle test means that you're going to have 3 samples, 2 that are the same and 1 that is different. And you want the people to be able to discriminate if they can tell which of those 3 randomly coded samples is the different out of the 3. So let's start really thinking about what this sample looks like from a theoretical perspective. So again, as I mentioned, 2 samples are the same and 1 is different. So the core question, are they different from one another? And when we set our hypothesis, and again, good sensory analysis, you are asking really important questions before you plan anything else. In this case, the core question is, are these 2 formulations the same or are they different? And we're going to set up 2 samples that are the same and 1 that's different. Now I have the order here A, and B. We're not coding the sample A, and B. We're coding the sample with a random 3-digit number. And we would have a set list so that the people who are preparing the samples behind the scenes know which samples are the same and which samples are different. So when I have the A, and B coding up here, that helps us within our set list to know which sample is the same and different. But the 3-digit numbers are the outward facing codes that are seen by the consumers. They would get their product, they would taste it, and if they were able to tell the difference, they'd be circling the odd sample. Now let's think this through a little bit more. Let's use our imagination. If the samples were really different, and now note here I have my A and B. Here's another thing. The sample shouldn't always be presented A, B. Sometimes it should be the B sample first and 2 A's, or A, B, and A. You want to randomize the order of those samples to different participants so that the order isn't always going to be the same and someone whispering to another, it's the last sample. You want to make sure that you're randomizing so that people really are having unique odds of being able to select. But let's say this was our sample. We've got A, they're the same, and B, as if just in case you can't see the color, we have 2 beige samples and 1 blue sample. And we have 2 circle samples and 1 oval sample. So this B sample down here it's pretty easy to be able to tell that it's the different sample. And so in this case, the odds of selecting the odd sample should be 100%. Now, if we think about if we're a really effective product developer, what would be the opposite direction? So I always say what we're doing right now is we're mentally thinking through the hypotheses to think about what this data would look like in advance of actually running the sample. But if we did a really, really good job on product development, Now we have pretty much identical samples. They're all beige, they're all circles. I'm assuming they're delicious. But again, that's not the question. The question isn't, are they delicious? It's, are they the same or are they different? In this case, the odds of selecting the odd sample now is 33% because, again, functionally, there's no differentiation between these samples at all. Sometimes people will pick the odd sample, and we have to be aware of that the odds are not 0% that they're going to pick the odd sample. It's 33% because the potential of them picking the B sample is random odds at this point. And so we can't just be focused on the percent. We have to be thinking about the percent, but also the confidence in the data. And we have to be thinking about the population size that we're working with. If we've only got 10 people participating, the likelihood of people guessing are pretty high, but we're going to be converging better if we have 100 people participating. But the odds of them picking the right sample are slimmer here. Now, how do we pose the question to the participant? They're not seeing that A or B code. That's on a set list. They're going to get a questionnaire. Now, running sensory analysis, more and more we're seeing people put their questionnaires onto computer tablets, or they'll have a sign-in code when people come to participate where they can open up their smartphone and be able to enter the data into a survey tool. But more often than not, going back old school, people will still have paper ballots. The questionnaire is usually pretty straightforward. Now, typically we would have had a risk pre-screener. So let's say we were having I think beige circles. We're not going to eat beige circles, but maybe they're vanilla cookies. We should be listing the potential allergens on those cookies. So please be aware that if you're allergic to the ingredients listed here, wheat, eggs, milk, etc., please do not participate. We value your health and wellness. You can also indicate that food products are being handled using good food handling practices and safe food hygiene fundamentals as part of the pre-screener. But once they're in there participating, you're going to have a questionnaire that's asking the questions. Please observe, smell, and taste the products in front of you. Identify which sample is the different sample. You may use water and crackers to cleanse your palate. Remember, there's no wrong answer, and if you are unsure which sample is different, please guess. And then have this grid here saying place an X in the box of the sample you feel is the different sample. And they can go along and answer X. How does this look in real life? Well, here's an example of a tray that we had set up. So you'll note, in this case, we did the questionnaire, and we actually made a placemat out of that questionnaire. And what you can't see under the samples is that we also had those are pricing gun tags. We had the pricing gun tag, and it just happens to be obscured underneath the cups here. But we turned the questionnaire into a bit of a placemat as well. So they were presented with the 3 samples, questionnaire. We also can't see that there's a pencil over here. In this case, with the paper ballot, do make sure that you have a pencil or a pen available to your participants. We've got the unsalted crackers and a glass of water so that they can cleanse their palate. Or cleansing your palate just means you're removing any flavor that you may have had from tasting the previous sample. And in this case, it was orange juice. And we were doing this in class, and it was a co-packer changeover for national brand orange juice. We were able to tell that it was a private label orange juice at a national brand, and we could tell that it had changed co-packers because the labeling and the bottling had changed over. We wanted to see if we could tell the difference between these products. So let's imagine our participants took their trays, they participated, and they filled out the questionnaires, and now we're getting these questionnaires back, and we have to take a look. We need to remember what our set list is, and that set list is the list held back by the people preparing the samples so that we can go and interpret what these questionnaires are. So in this case, the set list may have indicated that 341 was the odd sample. And in this case, the participant did not identify the difference. But now let's say we've got a second questionnaire, because again, we usually have around 20 to 50 participants. So you've got 20 or 50 of these forms coming in. Some people will answer correctly, some people will not. And so we want to note this person did identify the difference. At this point, we're going to create a tally form and identify who identified correctly and who didn't. Now, if it's an internal team, you may know exactly who your participants were. In other cases, you may be blinding the names of the participants. In this case, I had an internal team. This just happened to be a list that we did in class, along with some random names of people that I know. And we made up our list, and we've identified how many people participated. So in this case, we had 15 participants, and we noted how many people correctly discriminated the samples. So we had 11 out of 15 people discriminate the samples. Now, it is tempting to just go along and say, oh, 11 out of 15 people, or 73% of people identified the correct sample. But we have to remember that some of these people were also likely guessing. And so it is important for us to go and do a bit of a statistical analysis. But again, I promised you at the beginning of this video, not a lot of hard math. So we're going to use some data tables that are provided by a wide variety of different sources. But these triangle test data tables are going to help us understand how confident we are in our data. So this is an example of one of these data tables, and I'm going to parse through what this means. But we already identified that we had 15 people participate, and remind me, I think we have 11 people get the right difference. So something worth noting in these tables. Check this out. If we do, I'll explain to you what the significance means in a moment, but 0.1 significance, if we have 10 panelists at 0.1 significance, that's 9 out of 10. That you need 90% of people to correctly discriminate the samples to be confident at 0.1%. 0.1% error. But wait a second, if we're up to 20 panelists, now we only have to have 14 out of 20, or 70%. This is where the bigger your participant group is, the more confident you can be in the data, and the more you don't have to have quite as large a population scoring correctly to be confident in that data. So the larger your population, the more power you have behind your sample size. However, the larger your population, the more it's going to cost to run that analysis, the more time you'll need, the more supplies you'll need, the more labor and helpers you'll need to pull it off. So this is the balancing act that, again, that 20 to 50 sort of is the sweet spot that most analysts have said is where they're comfortable. Now, what does significance mean? And so going back to this table, we see 5%, 1%, and 0.1%. In essence, this is where you're thinking about the potential that you made the wrong conclusion. And so how much percent-wise are you willing to say, maybe I made a mistake? These are what we call type 1 and type 2 errors in hypothesis testing. And so that p-value, some tables will call it a p-value, and you'll see it in a decimal form. And other tables will call it a significance value, and they'll express it as a percent. But it will help you determine how much false information you want to tolerate. And so just to illustrate what these type 1 and type 2 errors are, they're the false positive and false negative results. And so in this case, take a look at this. We've got 3 ice cream cones here. I know that it should be 2 the same and 1 different, but I couldn't find a stock photo that was 2 the same and 1 different. So pardon me for flibbing here, but we've got 3 ice cream cones and they're different. We've got obvious differences here. Whereas over here, the ice cream cones are the same. This is a true negative when we conclude this is not different. But if we were to somehow conclude that these ice cream cones were different, or these ice cream cones were the same, That's where we've got type 1 and type 2 error going on. And going back to this table, this is how much percent we're willing to put up with that could be potentially that error. So in some cases, we're okay with 5% error. In other cases, we may be only okay with 0.1% error. If the decision that we're making, we're okay with a bit of wiggle room, we may say that 5% is acceptable. But if we're a major national brand and we're making $1 million decisions, we may want to make sure that our data is in this 0.1% range. So again, that's where the significance means. And we noted already that that significance isn't just strictly correlated to percent. It is also taking into account that guessing that takes place in this type of study. So let's do some example data analysis here. So go back to our original data. We had 15 participants and 11 people correctly discriminated. So let's walk through what this looks like. We're going to find the number of assessors was 15. And, oh, wait a second, we're somewhere in between here. That's okay. We are just going to say it is less than 1%. But we can't say it's 0.1%. We can safely say, though, that it is less than 1%. Because 11 is going to be in this space in between. Now, different data. Wait a second. Whoa! Now we've only got 5 people who got it right. And you're likely saying, well, wait a second. How on earth do you interpret this? You can do it one of two ways. You can either say the data is not significant, or you can flip it and say, based off of the fact that we have 10 people who could not discriminate, we are confident at the 1% level that the samples are the same. Does that make sense? We flip the data. 10 out of 15 people did not guess. Therefore, 10 out of 15 people, if they did not guess, it means that they think that the samples are the same. And so you pat yourself on the back if you were the product developer. It means that you did a really good matching job. And at 1% level, you can be confident that the samples are the same. So let's just summarize that. The first test, we had 11 out of 15 people able to taste a difference. And so we kept the data as is. 11 out of 15 could taste a difference with less than 1% error possible. The second test, we had 5 out of 15 people able to taste a difference. And in this case, we flipped it. So 10 out of 15, or 66%, could not taste a difference with 1% error possible. I always say go back to your gut common sense. Really think about what that data looks like and what does an individual result mean. And so if we go back and jump back and say, if Hassan was able to tell the difference, what does that mean? It means that 1, 2, 3, 4, 5 people could tell the difference. 5, go back to those percents. Those percents, while they're not the whole picture, help really give the intuition behind how to do this data analysis. So again, I often teach this course to people who are not mathematicians, people who in many cases are actually shy of math. And as such, we can do a lot of this math thinking really about the intuition behind the samples. Now, what happens is if you've got something like 7, and even if you flip that data, that just means that you really have an ambiguous sample and that you can't be confident that it's different. And flipping the data is not going to help you one way or the other. So let's revisit this again. Now that we have a better sense of what the test does, it now makes a lot more sense why product developers might be using this. So in the case of, for example, these Pringles sodium, Pringles, it's a major internationally recognized brand, and people have a really strong sense of what they're going to be expecting if they were getting a Pringles product. And suddenly, if they have a low sodium product, they will still want to have a similar taste experience. Similar with this Minute Maid calcium with vitamin D. Again, a brand that has a strong identity, but they don't want it to taste like calcium and vitamin D. They want it to taste like their flagship orange juice. And so a difference test would be really critical for the product developers to ensure that that formulation is the same. The no-name mac and cheese, they're up against a major national brand, likely Kraft Dinner, to make sure that that product is performing as close as possible to the competitor. And the Coke we mentioned before, they're trying to make sure that the different sweetness profile actually matches the flagship Coca-Cola brand. So now it's your turn. I think that you are, at this point, capable of trying it out. And so I encourage you to jump right in, test out your capabilities of running a triangle test, and have some fun with this. It's a fun entry point to doing sensory analysis, and I hope that you have a good journey learning more about sensory analysis as we go along. Take care, and we'll talk to you soon.